An FM signal with a frequency deviation of 10 kHz at a modulation frequency of 5 kHz is applied to two frequency multipliers connected in cascade. That means, and the first multiplier doubles the frequency and the second multiplier triples the frequency. The modulation index of the FM signal obtained at the second multiplier output is, here this is the FM signal. According to the question, it is having delta F, that is 10 kHz, FM is 5 kHz. So it is passed through a cascade connection of two multipliers, that is first one is doubles the frequency and second one is triples the frequency. So here what happens is, when we are passing a FM signal through a multiplier, only deviation gets affected. The modulation frequency is not going to be affected. 2 delta F, this is FM as it is. Here is 6 delta F, FM is as it is. We have to calculate the modulation index at the output of the second multiplier. We know that in case of an FM, that is frequency modulation, modulation index beta equals to frequency deviation divided by modulation frequency. Here the frequency deviation is 6 del F, means 6 into 10 kHz and 5 kHz. That is nothing but 12. Hence option A is correct. A DSB-SC modulated signal is transmitted over a noisy channel with PSD shown below. The message bandwidth is 4 kHz and the carrier frequency is 200 kHz. The average power of the modulated wave is 10 watts. After the coherent detection, output SNR is. Here the DSB-SC spectrum is given as follows: double sideband suppressed carrier. Here this is bandwidth is 8 kHz, because the bandwidth in case of DSB-SC is nothing but 2 FM. FM is the bandwidth of the message signal, that is 4 kHz, it is 8 kHz. It is distributed around center frequency, that is 200 kHz. Here also in similar way, that is this is minus 200 kHz and the bandwidth is 8 kHz. So if we are passing this signal through a channel which is having a PSD in this way, means the signal is going to be affected in this way. Here this is the PSD of the channel, this is 400, means exactly middle we will get 200 kHz. The signal bandwidth is 8 kHz. Here also this one, this is minus 400 kHz. So exactly middle way we will get minus 200 kHz. The magnitude is 10 power minus 6 watts per hertz. So here it is a linear variation over the top of this portion. So we can approximate it to the average value, that is in this way. So this magnitude is at 200 kHz we have to calculate. This is a linear portion. So if we calculate, we will get here is 0.5 into 10 power minus 6 watts per hertz. Okay. Hence here first of all DSB-SC signal x of t is AC m of t cos omega ct. So after passing the x of t through the channel, we will get x of t plus n of t. Whereas n of t, it consists of two components. One is the in phase component and the quadrature component. So this is detected through a coherent detection. That means the quadrature component is get eliminated. So the resulting signal y of t, if we assume ACM of t plus Ni of t is the output of the receiver. Okay, the power of the, this is the signal component, this is the noise component. Here the signal power already it is given in the problem, that is because this is the modulated wave. Okay, signal this power is AC square P by 2, which is 10 watts. The noise power is given as noise power equals to twice into 0.5 into 10 power minus 6 into 8 kilohertz this. So it is around 8 millivolts. So signal component by noise component, that is SNR at the output of the DSP-AC receiver is 10 by 0.008. So if we apply the logarithm, that is in dB, we will get it as 31 dB. That is option A is correct. Question is, let a message signal M of t be transmitted using single sideband modulation. The PSD of the M of t is given below, where A and omega are constants. AWGN of 0 mean and PSD equals to N0 by 2 is added to the SSB modulated wave at the receiver input. So the output SNR of the receiver is, here we have to find out the signal to noise ratio at the input of the receiver. Signal to noise ratio at the input of the receiver. That means, see, the signal power, that is P is nothing but integration 0 to omega A F by omega A by omega are the constants. So A by omega, the F square by 2 0 omega. So these two gets cancelled. Here A omega is the signal power. We have to find out the signal to noise ratio at the input of the receiver. So at the input of the receiver, the signal is nothing but an SSB signal, which is whose standard form is, that is SSB signal S of t is M of t AC cos omega CT plus or minus, means plus for LSB, minus for USB, that is upper sideband, AC M cap of t sin omega CT. This is the standard form of the SSB signal. So the power of the SSB signal is this, after passing through the S of t through the channel whose PSD is nothing but N0 by 2 over the range minus omega to plus omega. So the power of the SSB signal is AC square by 2p plus AC square by 2p, which is equals to AC square p. Again, the noise power because of the channel is N0 by 2 and 2 omega, that is N0 omega. Here P is nothing but a signal power, which is A omega, AC square A omega. Now signal to noise ratio is nothing but signal power AC square A omega divided by N0 omega. Omega omega gets cancelled. The signal to noise ratio at the input of the receiver is AC square A by N0. Hence option D is correct.